where we were on Wednesday. All right, so when we talk about functions, we're talking about a mapping that takes a value out of the domain. In this case, that's the oval on the left. And we make an assignment to a value in the range. And so f at a equals b in this kind of setup. And so we talk about the inverse as being the mapping going the other way. We're going to take a function f inverse at b and map it to a.
Are these anti-derivatives?
No. We're not talking about derivatives at all. We're talking about function inverses. Okay? So it's confusing because derivatives are primes and we have a -1 as a superscript when we're talking about inverses. Don't confuse that with the reciprocal. If we want the reciprocal of a function, we put the whole function in parentheses and then put the -1 because then it's an exponent. Okay? Because f is a function, and when we use the superscript of -1, that means inverse. But if we take f at x, which is a value, if we can take the reciprocal of that by making a superscript on the outside of that. So there's a little notation difference that you have to be aware of. Okay, so not all functions have inverses. The classic example is x squared, where if we take f at x, if x equals 3, then we get 9. If x is -3, then -3 squared is 9. There can't be an inverse because what does the backward mapping do? If you say f inverse of 9, what does that equal? Well, it could possibly equal 2 values, but since it could possibly equal 2 values, that violates the most important definition or the most important characteristic of a function is that you get exactly 1 value out of it. So we don't have an inverse in this case. Okay, so we have two tests that involve lines when we're looking at graphs of functions that will tell us. The vertical line test is if I put a vertical line through a function or through a candidate for a function, if it only crosses in one place, no matter where I put that line, it's a function. We have this horizontal line test, which is similar, except that we're going to use a horizontal line instead of a vertical line, and this will tell us if there's an inverse or not. So if we look at the function x cubed, I can move that red line anywhere, and I can convince myself by moving that red line back and forth that x cubed is a function because it only crosses the red line once. The blue line, if I do the same thing, if I move that up or down, I'll only intersect the graph in one spot, so that tells me it has an inverse. And in fact, the inverse will look something like this. And at the end of the hour, we'll talk about what shape that inverse will take. Okay, so if I look at x squared, it passes the vertical line test. It's a function. But since the horizontal line will go through that function in 2 places, it doesn't have an inverse. And then, in fact, if I graph what would be the inverse, we know it's not a function because it fails then the vertical line test. Instead, what we have are actually 2 functions. We have the square root of x superimposed on the square root of, or the negative square root of x. So when you take the square root on a calculator, you know, if you take the square root of 9, push that button on your calculator, you don't ever get plus or minus 3. You always get 3. So we've defined the square root function as the positive square root. It would probably work if we defined it as a negative square root, but it would be forever driving you crazy with double negatives in there. So that's just what we define, and that's kind of a workaround for that. And so we'll see at the end also that if we limit the domain and the range, then we can get true inverses of functions with restricted domains. Okay, so we have two things about an inverse. If we take the composite between f and its inverse, we get the original value back. And if we do it the other way around, where we take the composite of f inverse and f, we'll get x back again. So let me demonstrate that with a function. We're going to get to how we actually calculate the inverse, or how do we formulate the inverse in a minute. But let me just show you how this works. That shouldn't be a prime. That should be a -1. See, even I make a notation mistake. It's easy when you're talking about derivatives all the time. Okay, this should be a -1, actually. How's that? Okay, so if I write the composite, the way I write composite functions is, I do this outer function, leave a space for my inner function, and then I'm going to fill in that blank with the inner function, and then do a little bit of algebra here, and I'll find that I get 1 over x, which is x. And so that completely goes through. Now, we won't worry too much about domain at this point, because there's some domain restrictions with both the function and its inverse, because there's a potential for dividing by 0. But we'll just assume that in its own domain, that thing simplifies out, the composition simplifies out to x. Yes?
Did you get that did you get the inverse just by multiplying by the conjugate?
No, I'll show you how we get the inverse in a minute. So if we do it the other way around, if we take the composite of the inverse and the original function, I write essentially a shell of my outer function. Where my variable goes, I'll write that inner function, and then do the same thing where I'm going to simplify here. I'll get x as well. Okay, so you can see right here that the numerator of this this ratio in the overall numerator, that simplifies to just x over, actually, did I do this even properly? Yeah, it simplifies to x over x plus 1, and then divided by 1 over x plus 1, that simplifies to just x. So it's a way to prove that you have an inverse, is to stick one function inside the other, and it should simplify to x. Okay, so here's the procedure for finding a function's inverse. So let's take that function, and I'll show you how I got that inverse. So first thing that you do is you abandon the notation, the function notation of f at x, and you just put in a y, because this is going to make it a little less cumbersome for you. Okay, so I write this in terms of y, and then what I do is I swap x and y. And at this point, what I'm doing is I've made my inverse in a sense. Okay, I just don't have a good expression for it. So what I'm going to do now is that I solve for y. And so when I solve for y, I get my inverse. Now, occasionally with these ratios, it's a little tricky. You have to kind of resort to collecting variables and factoring and things of that sort. And you'll have a couple opportunities to practice that now and with homework. But it's just straightforward algebra at this point. So then at this point, what we do is we rewrite it as an inverse, and so there's our inverse. So it's those steps. Write it as an x in terms of y equals something, swap the x and y, solve for y, and then you have your inverse. Now, if you get into something, like if you're taking the square root of a square, that's when you start introducing things like absolute values, and you're starting to get more than one value, and that's where this breaks down. So if you do it carefully, somewhere it should tell you that there's no inverse. And it's generally when, for our purposes, when we have a root. Yes?
Would you get it wrong if you left it 1 over x minus 1?
No, certainly not. I mean, I'm just showing you the form that, certainly 1 over x minus 1 is a perfectly good expression for that. I just wanted to get to the form, okay? Now, the other thing is that this is now a rational function, okay? And this is, strictly speaking, a rational function, but it's not in the form that you're used to. This would be harder to graph perhaps than this. This one you can tell what the long-term behavior is simply by the rules that we've established with ratios of polynomials.
So this only works if there's one x and it does not have a power.
Oh no, it works. It works in general. Okay, if we had, and I think I have some examples where we're going to use a cube actually in the example, so you'll see what happens there.
Okay.
Okay, so in fact, I'd like you to try this. So that's x minus 2 over x plus 3. Okay, so first thing is we write it as y equals x minus 2 over x plus 3, and then we swap our x's and y's. And so here we have two instances of y because we had two instances of x before. Now what we want to do is solve for y. And so the first thing we do is we multiply both sides by y plus 3. Okay, and then what we're going to do is expand the x plus y plus 3x, expand that parentheses on the left. And now, and here's the key to this, is we're going to put the y's on one side of the equation because that's what we want to solve for. Now we have xy minus y, and that factors. Okay, so that factors into x minus 1 times y, and we get negative 3x minus 2. And so now by division, we can get y equals 3x plus 2 over x minus 1, and therefore our inverse then is minus 3x, or the negative fraction 3x plus 2 over x minus 1. Okay? So now that you see it, it probably doesn't look hard, but the part that takes a little bit of insight is this step right here, where you're collecting all the y's to one side. And so that's the key. So when you have different terms involving y, think, I'm going to gather them all, and then I'm going to factor it out, and then divide by what I've factored.
So I do want to make sure. So for every single x, I just put a y there, no matter what.
Swap x and y. Okay, any other questions on this? Okay, so now if we wanted to be really fussy about checking, is this really the inverse, I would substitute the inverse into the original function. But a quick way to do it is to check a value, because oftentimes evaluating something to a number is fast, and if you've made some boneheaded, algebra mistake, which we all do, me especially, you've seen me make sign mistakes and things of that sort, you can just stick in a value and see if the value comes back at you. So in other words, I'm going to just arbitrarily, just because I want to choose a 6, and then I evaluate f at 6, I get 4/9, and so I put 4/9 in the inverse, and so I find that then will, with a little bit of calculation, I'll find that I get 6. And so what I've shown is that f at 6 equals 4/9, f inverse of 4/9 equals 6. And that's what an inverse is all about. You go one way with the function, you go the other way with its inverse. All right, now let's talk about domains and ranges, because this is going to be one of the things that helps us a lot in terms of not only finding inverses, but also finding domains and ranges, because I think you've found that it's fairly easy to determine the domain of a function, right? It's all the places where we're not going to divide by 0, and it's all the places that we're not going to take the square root of a negative number. But the range is a little bit more elusive, generally. You have to either make a graph or do something else to figure out the range. So when you think about it, remember that f at 6 equals, what was it, 4/9? And vice versa. the domain of f is the range of f inverse, and the domain of f inverse is the range of f. So we have a very mechanical way of finding an inverse. And so if we want to find the range of a function, what we can do is take the inverse of the function and find that domain, okay? Because we can very easily find the domains of functions, find domains easier than ranges. Okay, so in our in the function x minus 2 over x plus 3, the domain is all real numbers except x can't be negative 3, right? Because then we get division by 0. So what's the range of f at x? That's a little harder to say. So what we do is we calculate the inverse. And so here it says the domain of this inverse is that x can be any number except 1. So since we have the domain of the inverse, now we know the range of the function itself. So we can say the range of f at x is going to be all real numbers except y can't be 1. So think about with this function now we have those horizontal and vertical asymptotes. And remember what the vertical asymptotes say. That's the discontinuities in the domain. So our vertical asymptote of f at x is going to be x plus 3, or it's going to be x equals negative 3. Now the horizontal asymptote you can get with that function by saying, okay, it's the ratio of two polynomials that have the same degree, so it's going to be the ratio of the coefficients, which is 1. So your horizontal asymptote, the place that the function is never going to yield a value, it'll get close to it, but never there, is y equals 1. And we found that confirmed by the domain of the inverse says that x can't be 1. So when you translate that into the range of the function, then we have the horizontal asymptote. So the vertical asymptotes turn out to be the horizontal asymptotes of its inverse and vice versa. Okay, so let's go back to f at x equals x squared. So the domain of this thing is all real numbers, and the range, we're always going to get a positive number out of x squared, or 0, right? We're not going to ever get a negative number. So since the domain of the inverse is the range of the function, what we can do is say, okay, I'm going to limit my domain. I'm going to restrict my domain and range to see if I can get an inverse with a restricted domain. Okay, so what I'm going to say is that f at x equals x squared. F at x squared is always greater than or equal to 0. And so I'm going to calculate an inverse of this thing, where y equals x squared. And of course, y is always greater than or equal to 0. And so when I swap x and y, what I get is the square root of x equals the square root of y squared. Now, normally that would lead you to the square root of x is the absolute value of y, right? But since since from the beginning I've said my y is always greater than or equal to 0, I really just have one equation that comes out of this, that the square root of x equals y. All right, so if I can say that the range of my inverse is all numbers greater than or equal to 0, then what I can say is I can put a restriction on my domain of f. Reminds you that the domain of one is the range of the other. So if I make my function f at x equals x squared, where x is greater than or equal to 0, then I have a true inverse. Then I can say, okay, the inverse of that is going to be f at f inverse is going to be the square root of x. So I didn't make a graph of this thing, but I can sketch it for you very quickly. So I'm saying, instead of making the whole parabola, if I'm going to say x is always greater than or equal to 0, this function passes both the vertical and horizontal line test. So if this is f at x equals x squared, where x is greater than or equal to 0. Then I have this thing here, where my f inverse equals the square root of x. And of course, what's suggested here with the square root of x is that my domain of that inverse has to be x is greater than or equal to 0 as well. Yes?
So if you did the other side of the parabola and then the other side of the parabola again, you'd get the sideways u that isn't a function.
Well, you could get, what you could do is, if you wanted to define your function as this side, you'll find that the inverse goes like this.
Yeah, so you get that sideways u that
Yeah.
isn't a function. That's interesting.
Okay, so, and that's a matter of definition. This one is not so useful, but this one is extraordinarily useful because that's what your calculator does, right? If you want to find what the square root of 9 is, you have a function on your calculator that says the square root of 9 equals 3. And so if you try and take the square root of -9, you're going to get an error. And if you're going to say, okay, x squared, so long as you keep x positive, it does have an inverse. Now, when you get into trigonometry, you're going to have inverse functions of the trigonometric functions, like the inverse of tangent, inverse of sine, inverse of cosine. We call that arctangent, arcsine, and arccosine. You're going to find that those, strictly speaking, don't have inverses, but if you restrict the domain, you're going to find that you have inverses for your trigonometric functions. You'll learn that in 14, Math 14. Okay, so I'd like you to try something here. I'd like you to try and find the inverse of this. Okay, so let's see how we would calculate that, that inverse. And so I'm going to write it as y. Then I'm going to swap my x and my y. I'm going to solve for y now, and this works. The cube root works because I don't have to worry about any kind of domain restrictions. And so I get this thing that looks like cube root of x minus 1 plus 2. And so there's my inverse. Now, the graph of this thing looks like this. Look at the red line here for the function, and you see how that's kind of a displaced toolkit function of x cubed. And so, you know, this is, it's moved up 1 and to the right 2 if I look at this inflection point here. Now, if I graph this, I'm going to get a curve that looks like that. And one of the ways that you can kind of estimate what the inverse of a function looks like is you have this line of symmetry. And so the way you can sketch an inverse is just to rotate your paper by 45 degrees and then just make a mirror image of what you've seen. So kind of, I can't rotate this on the screen, but if you kind of cock your head over 45 degrees, you can see that one is the mirror image of the other with respect to that symmetry.
And it's always 45 degrees?
Yeah, because what we're doing is we're swapping x and y. Okay, and that's what, when x equals y, that's the equation of that line.
So x equals 1 on one and then y equals 1 on the other.
Yeah. Okay, so I'm just going to march through this example and then we'll finish. I was actually going to have you try to find the domain and range of this particular function. And so the way that you would do that is, of course, by inspection you can find that the domain x can't equal 2. And then if we find the inverse by swapping x and y and then solving for y, and here again I'm going to put all the y's on one side and then factor out the y. And so I have my inverse here. And so I know now that the domain of the inverse is going to be x can't be 3, so I know that the range of the function is going to be y can't be 3. There's no way that you can set that function equal to 3 and find an x that conforms to that. So think about asymptotes here. You know, you can get that asymptote. The horizontal asymptote is y equals 3. The vertical asymptote x equals 2. And the inverse function has it exactly the opposite, where you have the vertical asymptote as x equals 3. The horizontal asymptote, in this case, would be y equals 2.
Wait, hold up, I thought the domain and the range were like one-to-one swap, and there you've got x can equal 2, and then up here, both of them.
Right. So here I'm looking at the domain of y, of f at x, and here I'm looking at its range. Okay, so the domain of the inverse function is the range of the original function. Okay?
All right.
So think about that. Think about it in terms of asymptotes.